Right, what I want to do in this video is calculate the total capacitance and the total energy and the charge on three capacitors connected in series. I have capacitor C1 in series with C2 in series with C3, and these are across a supply. We'll call it Vs, and Vs equals 10 volts. Let's make C1 equal 0.2 microfarads, C2 equals 0.5 microfarads, and C3 equals 0.4 microfarads. To add them together we need the reciprocal method, so we'll call it the total capacitance CT. That'll be equal to 1 divided by 1 over C1 plus 1 over C2 plus 1 over C3. Whoops, 1 over C3. I'm trying to go too fast. And with our values, that'll be 1 over 0.2. I'm not going to put 0.2 to the times 10 to the minus 6. I'm just going to put them in microfarads, and then I can expect the answer to come back in microfarads. So that's plus 1 over 0.5 plus 1 over 0.4. And if I put it into the calculator, that gives me I'm going to use this button here, x to the minus 1, which means 1 divided by, or reciprocal of. So I'm going to put in 0.2, my first value, 1 x to the minus 1, plus 0.5 x to the minus 1, plus 0.4 x to the minus 1 equals, that adds up together to the values on the bottom. Now to divide it into 1 again, so press that button one more time, and that gives me 0.105 to 3 decimal places microfarads. The answer is microfarads because I put microfarads in. I now need to look at the total charge on the circuit. Now Q is the symbol for charge in coulombs, and it's equal to C times V, where that's the capacitance. Whoops, just rewrite that, C times V. C is the capacitance and V is the voltage. So the total charge on the circuit, QT, will be equal to the total capacitance circuit, which we just calculated, times the voltage of the circuit, which is 10 volts. So that equals 0.105 microfarads times 10 volts, giving us 1.05 microcoulombs. Microcoulombs because we used microfarads. Now we're going to look at the voltage across each capacitor. Now this interesting thing in a series circuit is that each capacitor has the same charge on it as the total circuit charge. So C1 has a charge of 1.05 microcoulombs, so does C2, and so does C3. So if I rearrange the equation, V for V, if Q equals C times V, divide both sides by C, cancels on this side leaving me with V, will be equal to Q, QT, divided by the capacitance. So if I want the voltage across C1, let's call it V1, I divide by the capacitance C1, which would be equal to the total charge, 1.05 microcoulombs, divided by 0.2 microfarads. And micro divided by micro will cancel, I get an answer in volts, and the result of that comes out at 5.25 volts. The voltage on capacitor 2 will be equal to the total charge divided by capacitor 2, so that's 1.05 divided by 0.5, and that comes out at 2.1 volts. Let's just make these nice and clear, and just move up a bit so I can stay on the screen. V, the voltage on capacitor 3, is 1.05 divided by 0.4 microfarads, and that comes out at 2.625 volts. These should all add up to 10 volts, and approximately do, except allowing for a very small amount of error due to the rounding that I've done. Right, the energy in the circuit, E, is equal to a half CV squared. We square the voltage, multiply with the capacitance, and then half it. Now for the E1, that would be the energy in capacitor 1. That will be a half times the value of capacitor 1, which was 0.5 microfarads, times its voltage, which we know is 5.25 volts squared. 5.25 squared. And as I'm putting it in microfarads, I'm going to get an answer in microcoulombs. And that comes out at 2.77 microjoules. Sorry, not microcoulombs, microjoules. It's amazing how many mistakes you make as soon as you start recording. E2 equals a half times 0.5, the capacitance of C2 times its voltage, which was 2.1 squared, and that comes out at 1.1025, quite an inconsistent number of decimal places here, and that's microjoules as well. And then E3 equals a half times 0.4 times its voltage, 2.625 squared, and that comes out at 1.38 microjoules. I ought to really have more consistent number of decimal places, but they're all approximate values. If I add all of those together, and again allowing for a certain amount of rounding, I get about 5.25 microjoules. I can calculate the total energy in the circuit if I use the total capacitance, which we found up here, multiplied by the voltage on the circuit squared, which was 10 volts, and then half that. So ET, we'll call it, total energy equals a half times 0.105 microfarads, the total capacitance, times 10 volts squared, and that also comes out at 5.25 microjoules.